Swayam Prabha. Digital India. Educated India.
Welcome to the 11th lecture in our particle characterization course. In the last lecture we were discussing particle size distributions, and we noted that size distributions can be obtained in essentially a tabulated form. Most particle counters will give you a count of particles by size in various size channels. They will report differential counts of particles only in that channel, as well as cumulative counts of all particles that are larger than a particular size. And we noted that these data can be analyzed statistically to obtain various mean particle sizes, and also that there are certain particle size distributions that occur in nature or due to specific manufacturing processes that are employed. And the three most common distributions are the normal distribution, log normal distribution, and the power law distribution. Again, it is important to realize that differential counts and cumulative counts are very important in controlling many different processes, but in terms of which one we actually use for a specific application, it depends on the sensitivities that are involved. For example, when we talk about atmospheric aerosols and their health consequences for people, now typically what we care about are particles that can be ingested into our system. Our noses are actually excellent filters, so they will typically not allow large coarse particles to enter. It is the finer particles that can actually penetrate through our mucous membrane and actually enter our lungs or our digestive system and so on. So in this case, the most relevant particle count is all particles that are smaller than a certain size, because there is usually a minimum size of particles that can be retained in your nostrils, and any particles that are smaller can penetrate through and enter your system and possibly cause harm. So an atmospheric scientist would be typically interested in particle counts that are smaller than a specified size. On the other hand, if you look at a process like microelectronics manufacturing, there is a clear correlation that has been established in the industry over time regarding the size of contaminant particles and the probability of causing a defect in the product. And here it turns out that any precision product or microelectronic product has a threshold size above which a particle will cause a failure, but below which the particle is essentially benign for the product. So every product, whether it is a wafer or whether it is a hard drive or whether it is an integrated circuit, they all have these characteristic threshold dimensions below which no harm is caused by the particle, but above which the defect probability quickly rises to 1. So in such a situation, obviously a contamination control specialist, someone who is looking after the health of the product from a particular viewpoint, would be most concerned about all particles that are larger than a certain size. So in that case, the cumulative counts become very important. So the key thing to remember is a particle counter gives you a lot of data. You have to be careful in selecting which data are the most relevant and most appropriate for your process. Now dealing with discrete data is always difficult because of the discontinuity in the data. Dealing with tables of numbers is always more difficult than dealing with a function, an equation, or a graph, right? So you always want to convert this set of discrete data into a continuous function. Now, when you try to represent particle size distributions by a continuous function rather than tables of data, the error involved in such a procedure is directly related to the number of particles that you are actually counting in your system. As the number of particles increases, the relative error in assuming a continuous function decreases. For highly dilute systems, it is very risky to interpolate and fit a functional form to a set of data, because the uncertainty in the data in a particle counter increases with a reduction in the concentration of particles in the fluid that you are measuring or on the surface that you are measuring. And so, the representation by a continuous function must be done carefully, but when it can be done, it does enable you to fit a model to a distribution, which then allows you to do various interesting things in terms of optimizing the particle size distribution. Again, in some cases you may want to push the particle counts to a lower size, in some cases you might want to push it to a larger size, or in some cases you just want to establish a very tight control over the mean of the particle size. So, when we try to fit particle count data using a function, now typically the counts are given as a size range or delta in the particle size versus a differential count delta n, right. So, for various values of delta dp, we get values of, let us say, the differential count of particles in that channel. Now, how do you take this data and convert it into a continuous function form? Well, one way to do that is to define something called df, which is a frequency function. It is the fraction of particles in a particular size range. So, you can look at this as delta n over n corresponding to any value of the particle diameter dp, where delta n, or you can even represent this in differential form as dn, corresponding to this differential channel between dp and dp plus ddp, divided by the total number of particles n. Now, what you can do is you can represent this dn as dn by ddp multiplied by ddp. So, simply dividing and multiplying by the same parameter ddp, which is a differential in particle size corresponding to that channel. So, when you introduce this into your equation for df, this becomes dn over ddp over n times ddp, and this parameter dn over ddp divided by n is what we will simply call f of dp times ddp. So, the final equation that we come up with is that df, which is a fraction of particles in a particular size range, is the frequency factor f of dp, which relates to how many particles are present in a particular size range multiplied by the width of the size range itself. Now, once you have established the value in this form, integral of df from the lowest measurable value to the highest measurable value must be equal to 1. Now, as we saw yesterday, when we have a log normal distribution, you are better off using geometric means as well as logarithmic values. So, in that case the formula in this particular instance would be that for a log normal distribution you would use df equals some f prime of dp times d ln of dp. So, you would use this formula essentially for a normal distribution, and you would use this formula for both a log normal as well as a power law distribution. And in that case your integral of df would still equal 1 whether or not you are dealing with a normal or a log normal distribution. Now, suppose you want to know all particles that are, let us say, between sizes a and b. Now, in a differential table it is very easy to do. You essentially just take those two numbers and count all particles between them, but obviously you can imagine the difficulty that the sizes here may not correspond with the interval you are looking for, right. So, depending on the granularity of your channels you may not get the information you are looking for. For example, if the table is only giving you from, let us say, from point 1 to point 2 is one channel, point 2 to point 4 is another channel, and point 4 to 1 is another channel, but you really want to know the number of particles between 0.5 and 0.7, right. Obviously you cannot do that using the tabular form of the data. That is where continuous functions become important in order to be able to interpolate as well as extrapolate the data that you have. So, if you want to obtain that information, once you have formulated a function, it becomes simple. So, integral a to b of f of dp ddp will be the number between a and sizes a and b. Suppose you want to know all particles that are smaller than a size a. All you have to do is integral 0 to a f of dp ddp, and this would be the count that is smaller than size a. So, this is the kind of analysis that an atmospheric scientist would typically use, or a hygienist. Integral b to infinity of f of dp ddp, it gives you the count larger than of all particles that are of sizes larger than b, and this is what we refer to as a cumulative count. And again, in most manufacturing applications where finer particles typically cause you more problems than coarser particles cause you more problems than finer particles, this way of calculating counts is much more applicable and relevant. So, there is certainly a lot to be gained by fitting a continuous function to particle size distribution, but always be aware that your confidence level in your fit will be substantially increased if you collect more data. So, the more concentrated the suspension is, the better. However, there is an inherent conflict there, because laser scattering techniques are based on essentially principles of light scattering from a single particle, which means that the more dilute the sample, the better the accuracy in your measurement, right. So, you have to balance these two requirements. So, you want to get as concentrated a suspension as possible in order to improve the statistical accuracy of your analysis, but you want to keep the concentration lower than the limit at which coincidence errors start happening. Basically what would happen is, if you have too many particles that are too close together, instead of single particles being detected by the laser, you may have multiple particles that are essentially screening each other, and that is called a coincidence error, and that leads to a significant reduction in the efficiency with which particle counts are obtained in a light scattering type of particle counter. So, you have to balance that very carefully. The mean size statistics that we looked at last class for discrete data can also be obtained in this using integral formulations. For example, your dp number mean would be simply equal to integral 0 to infinity of dp f of dp ddp, and your diameter mean would be integral of dp squared, your area mean would be integral of dp cubed, and so on. So these are essentially the continuous function counterparts to the differential analysis of mean size that we discussed in the last class. And of course the variations or the standard deviations can also be calculated accordingly, both for the discrete form of data as well as the continuous representation of particle size distribution. So the key point in all this is that particle size measurement in its essence is a single particle measurement, particularly if you are using a technique like light scattering. But ultimately the use of particle counters and particle size analyzers is not for looking at a single particle, but rather an entire population of particles. So when you try to extrapolate the technique from usage for a single particle to an assembly or collection of particles, you have to bear in mind the fact that there are errors involved, and when you are trying to obtain a size distribution, as far as possible try to refer back to some standard spectra that are available, just like you do for if you have used FTIR spectroscopy, right. You obtain a characteristic of the material that you are looking at, but it is very difficult to interpret the spectrum as such. What you do is you compare it to a reference spectrum in a library, and then you identify that this material has a signature that is closest to this reference material in my library, so it must be that material. Similarly, when you obtain particle size distributions, as far as possible try to refer back to the standard size distributions and assign a distribution to a particular population of particles. This will enable you to also understand the mechanisms of formation of these particles, because as we discussed in the last class, each characteristic size distribution has a specific source or combination of sources associated with it. So the particle size distribution curve will actually provide you a lot of information, not only about the counts and sizes of the particles that are present, but also the history of how these particles came to be. So it's very powerful data, but it must be carefully analyzed and managed. Now I mentioned that one of the limitations of light scattering based particle size measurement techniques is the fact that they require a highly dilute sample. But in practice there are many suspensions that must be analyzed in a concentrated form. For example, if you are using a lubricant in a machine and you want to control the level of particulates in that lubricant to prevent wear of the machinery, for example, then you really don't have the luxury of diluting that material. You want to measure it as is. So when you talk about measuring suspended particles in a lubricant that's used in a machine tool, it's a highly concentrated suspension. Another instance of that would be, again in semiconductor manufacturing, there is a process called CMP, chemical mechanical planarization, where a slurry of particles is used to polish a surface to very high surface finishes. Here again in a slurry you are forced to use high concentrations of particles. It just won't work if you are using a low concentration. But if you take the slurry and try to dilute it in order to measure its particle size distribution, you actually change the properties of the slurry itself. In particular, parameters like the zeta potential could be affected, which can cause differences in the size distribution. So by diluting the sample, you actually change the size distribution characteristics of the sample. So this is another example where you don't really want to dilute the sample, but you still want to measure size distributions over a very wide range, ranging from nanometer to millimeters. Another example would be emulsions. Oil in water emulsions, various other types of emulsions are commonly used in many different applications. Now when you look at emulsions, again they tend to be fairly concentrated in nature, and they tend to have optical transmission characteristics that are very close to each other. In other words, when you have a particle in a fluid, the optical characteristics of the particle are very distinct from the optical properties of the fluid, so you can easily distinguish them. But when you have oil suspended in water, let us say, the optical characteristics are not so distinctly different that you can clearly say, just based on light scattering, whether this is oil or whether this is water, especially as the droplet size becomes smaller and smaller. And so in such cases, you really cannot use light scattering as a technique to measure particle size distribution. So what is our alternative? One of the techniques that's in widespread use is the use of acoustic waves to accomplish the same purpose. So instead of irradiating the fluid with a light source, essentially you transmit an acoustic field to the fluid. What happens? Well, you have to imagine this as essentially three phases that are being present now. You have the fluid phase, you have the particle phase, and then you have the sound wave that is propagating through this suspension. The particles that are present in the suspension act as discontinuities, which essentially interact with the sound wave that is progressing through the fluid, and they cause the sound wave to be scattered. Some of the sound energy is absorbed, but basically there is an extinction or attenuation of the acoustic field due to the particles that are present in the suspension. Now, and this is basically called acoustic attenuation. That's a name for the phenomenon that is going on. Now, what are the effects of this acoustic attenuation? A, some of the sound energy will get absorbed by the particulate phase that is present, and as that happens, there will also be a heating up of the particle. So a temperature gradient will develop between the particle and the fluid, and some of the sound energy will also be absorbed by the fluid medium itself, and again that can cause more of a macroscopic heating effect. So a lot of the acoustic energy gets dissipated through absorption either by the particles that are present or by the fluid itself, but some of the energy also gets scattered in various directions. So if you look at the transmission characteristics of an acoustic field, it should give you a pretty good idea of the particle concentration in the suspension as well as the size distribution of particles in the suspension, because just like with light scattering, acoustic wave scattering is also very much affected by the size of the particle, the shape of the particle, the concentration of the particle, and so on. So acoustic scattering is a technique which is superior to light scattering for concentrated suspensions, because unlike light scattering, which essentially requires a single particle interaction with the light source, in acoustic scattering you can actually transmit the sound wave through a concentrated slurry of particles, and you can still deconvolute the phenomena that are going on sufficiently so that you can still establish a particle size distribution. So this technique of acoustic attenuation is predominantly used for concentrated suspensions, but there are some uncertainties in the data. If you look at the effect of particles on attenuating acoustic light, you see a very interesting trend. If you plot particle size on the x-axis and a relative attenuation coefficient on the y-axis, what sort of trend would you expect? If you recollect, when we talked about light scattering, for example, as the particle size increased, the scattering intensity increased as dp to the power 6. So the attenuation also increases as dp to the power 6 in the case of light scattering. In the case of scattering of an acoustic wave, and we look at ranges of size here from let us say 0.001 microns to 0.01, 0.1, 1, 10, 100 up to 1 millimeter, right. So, this is from 1 nanometer to a millimeter, and let us say that these are relative values, and again they can range from 0.001 to 0.01, 0.1, 1 and so on. The trend that you see is interestingly enough cyclical in nature. Now, that is fine, I mean it just happens to be the way that acoustic waves interact with particles in a suspension, but the problem now is what you are measuring is this attenuation coefficient, right. So, when you look at that, how many possible values of dp can you predict for each spectrum. So, just draw a horizontal line and you can see that it is multiple, because if you are just measuring this, then this could be the size, or this could be the size, or this could be the size, this could be the size, right. So, there is a lot of uncertainty. So, based on a single acoustic attenuation measurement, you cannot conclusively say what the size of the particle is. Now, if you have some prior indication that this particle is in the nanometer size range, then yeah, I mean a single measurement and just look for a particular value that is in the size range you are expecting, and you can conclude that that is the actual size. But if you do not know anything about the particle powder that you are looking at, then there are multiple values. Now, this is for let us say a frequency ultrasonic frequency of 1 megahertz. So, how do you resolve this? How do you deal with this? And that is where this technique called acoustic attenuation spectroscopy comes in. The idea is clever. Basically say what we do is, instead of only transmitting the acoustic wave at a single frequency, we actually transmit a spectrum of frequencies all the way from typically from 1 megahertz up to 160 megahertz. Now, what will happen is at each of these frequencies you will see a different spectrum. So, this may be the spectrum corresponding to 1 megahertz. At a higher frequency you will see a greater attenuation. So, this may be at 10 megahertz, and so you keep going like this for as many frequencies as your system can handle. You can essentially have an infinity of frequencies that you transmit and measure at. Now, what happens? Again, if you use the same methodology and you are plotting Tp versus the relative attenuation coefficient, based on one frequency you may have detected possibly 4 different sizes. If you test at another frequency, then in principle, by the way, these peaks move to the left. I haven't sketched it very well, but as you increase the frequency, the peaks that you see slowly move to the left. In other words, there is a relationship between the wavelength of the light and the diameter of the particle that decides how attenuation happens. So, because of that, in principle, if you just test at 2 different frequencies and look for the one common diameter that is detected at the 2 frequencies. In other words, is there an when you again you look at the kind of the possible sizes corresponding to the second frequency, in principle there should be only one size at which there is convergence between these two. That is assuming absolutely no measurement errors and no possible intrusive effects that can affect your sound transmission and so on. In practice, it is not possible, and that is where the spectroscopic technique comes into play. As you keep increasing the number of frequencies that you test at and you keep measuring possible sizes that you obtain based at these various frequencies, eventually you will identify that one unique size that is present in all these spectra, and that you decide is the actual size of the sample of the particles in your sample. Now the limitation of what I just talked about is this only works for monodispersed samples, in other words where there is only one size. Now what happens if there are multiple sizes in the population, when you have a particle size distribution, can we still use this technique? Because each size particle will attenuate the acoustic signal differently. So the problem becomes multidimensional. However, there are mathematical inversion techniques that you can use to extract even the size distribution of a polydispersed population, but the procedure is a little more complex when you are dealing with multiple particle sizes. The first thing is, based on the physical mechanisms that are happening, you have to predict an attenuation spectrum. In other words, by using conservation equations of mass, momentum, heat, by using constitutive relations such as the equation of state, and by looking at the fluid mechanical properties, constitutive relationships such as stress versus strain relationship, and by using the wave equation that describes how a wave interacts with the media, you can actually predict for a hypothetical particle size distribution, you can predict how these attenuation spectra are going to look like. So that is a step number one. The step number two is you actually make the measurements, these measurements. You irradiate your sample with acoustic frequencies over a wide range, obtain the spectra, and then you compare the two and look for the difference or the delta. If the difference, if they do not match exactly, you tweak your model. So you take your experimental data as being absolute and you try to tweak your assumptions about the particle size distribution until you get an exact match. It may sound complicated, but mathematically it is not that difficult. There are algorithms which will essentially optimize the fit to get minimum deviation between the predicted particle size distribution and the measured particle size distribution, and that is the way it is done in practice. So companies that make particle size analyzers based on acoustic attenuation spectroscopy, for example Malvern Instruments has such an instrument. The equipment comes with a pre-built-in algorithm. So all you have to do is specify the fluid and specify the particle and specify the frequency range that you want to employ, and the size analyzer will immediately generate a prediction of the attenuation spectrum for a hypothetical particle size distribution. So it is all done for you. You do not, I mean the software already does the theoretical prediction, and then the instrument will do the actual size measurement by transmitting an acoustic field. It will then do the comparison, it will do the iteration. The whole thing will take about 10 minutes, and you will get a particle size distribution using an acoustic attenuation spectrum device. Again, the power of this technique is a very wide range, because this is very useful to us, right? There is no attenuation of the intensity by particle size. You can go from very small sizes to very large sizes without there being a significant systematic difference in the attenuation coefficient, unlike in the light scattering case, where there is clearly no way you can use light scattering for particles that are smaller than a certain size. Inherently there are no limitations to using this acoustic technique over a very wide particle size range. Now the limitation in this case is that it does not work well if you dilute the sample too much. So it is exactly the kind of the mirror image of light scattering based techniques, where the techniques do not work well if the concentration gets very dilute. So in fact correlation measurements have been done between the two types of instruments. So if you take the same suspension and you plot size versus count, and let us say that you are looking at a range from again 1 nanometer up to let us say 100 micrometer, So let us say you get some spectrum based on laser scattering. You take the same solution and you subject it to the acoustic method of monitoring. Will you get the same data? Yes, you will. So let us say that the acoustic device gives you this data. This is the acoustic attenuation spectrum based methodology. But what is the difference? The difference is with laser scattering you would have probably measured at a dilution of 1 to 1000 roughly. So the volume percent of particles in this may have been, let us say, 0.001% in order to get good data, but the sample that is used for the acoustic technique, the concentration can be as much as 1%. In fact, it has to be as much as 1% in order for the data to match. If you take this solution and you start diluting it, then you will see that the distribution you are getting in the acoustic device will start deviating from the distribution that you got in the light scattering device. Similarly, if you take the solution that you used for the light scattering measurement and you start concentrating it, you will see that it will start deviating from the measurements using the acoustic attenuation device. So you will never get exact coincidence at the same concentration, but you can get virtually the same data from the two instruments if in one case you dilute and in the other case you concentrate the sample. And in fact, the way that you want to use an acoustic particle counter is by determining the concentration at which you start getting stable values. So for example, what you should plot is something like concentration of particles versus the mean size. What you will find is that up to a certain concentration there will be deviations in the data, but eventually it will stabilize. So this is a characteristic behavior of an acoustic attenuation spectrometer for measuring particle sizes. If you repeated this in the case of a light scattering device, the trend you will see will be the exact inverse. So what you will find is that you get a behavior which shows significant deviation at the higher sizes, but gives you a very stable data at lower concentrations. Okay? So the stable size that is predicted by both methods will be very close, but if you are not careful you may have measured at the wrong concentration and got completely different values. Depending on the concentration, if you use the same concentration, then it is very unlikely that you will get the same data. In fact, there will be for the most part a significant deviation. Coincidentally, there may be a point where they coincide, but even that would not be the correct value, because this value is obviously not the right value. The asymptotic value that you see is the actual mean size, and that is why it is very important to understand the principles involved in various measurement technologies and make sure that we use the one that is appropriate for our sample. I mentioned that the acoustic size analyzer could be used for emulsions, and in fact some very careful quantitative correlation work has been performed using SEM-TEM image analysis and particle size measurement using acoustic attenuation, and you can see a virtual one-to-one correspondence between the particle size distributions that are predicted by the two methods. So it is a very powerful method. The usage of an acoustic attenuation spectrometer is not as widespread as light scattering, primarily because in most conventional applications you are dealing with dilute samples, but certainly in any situation where you have to deal with a concentrated sample, the acoustic based techniques will work much better for you. Okay, a a couple of other points that we should look into before we complete our discussion of particle size analysis. When we measure size of particles in a suspended, particularly in air, there are really three characteristic sizes that you can specify. One is what we call a primary sphere diameter, the second is agglomerate diameter, and the third is crystal size. Now this distinction becomes especially important as you start approaching the nano sizes. Nanoparticles have a clear tendency to agglomerate. So when you are trying to measure the size of a nanoparticle, it is very, very difficult to do so, because by the time you get ready to do the size measurement, it is already moved, found its nearest neighbor and attached itself to its nearest neighbor. So every time we try to actually measure the size distribution of a sample containing nano dimensional particles, what we find is what we are really measuring is not the size of the individual nanoparticle, but rather the size of a conglomerate of such particles that are adhered together. And even in the case of a single nanoparticle, the crystalline structure that is present within that particle is different in size from the particle as a whole. As we will see later on, the structure of a particle really encompasses three different regions. The crystal or the core is the interior, but there is also what is known as a subsurface region and a surface region, which act as the interface between the crystalline structure of the particle and its surroundings. And so these three sizes are important to characterize when we are trying to determine the shape, well, in particular the size of nanoparticles. So in the next lecture we will start out by discussing these aspects in a little more detail, because it is very important to understand if you want to extend our particle characterization technologies to the nano dimensions. In the next class we will also work out a few problems that illustrate some of the principles that we have talked about so far in our lectures. There was a question before the class from one of the students about textbooks to be used for this course. Now particle characterization is a very widely studied and researched area, so I would not recommend a single textbook to cover everything related to particle characterization, but a good book to begin with is the one by J.K. Beddoe. It is called Particle Characterization. It was written back in the 60s, I think it was reprinted once in the 80s. Beddoe is considered like the godfather of particle science, and many of the things that we have talked about in this course so far, particularly related to shape analysis and some of the size analysis methods that are based on direct inspection of particles, were actually laid down by Beddoe and his fellow researchers. So it is a very good textbook to read in order to understand the history of particle characterization. But some of the methods that we have talked about more recently, based on laser light scattering or acoustic scattering, are really not covered in that textbook. What I will do is, in one of the later lectures, I will provide you a list of references that will cover the various sources that I have taken my lecture material from. I also encourage you to read current literature. I mean, there are a lot of publications in journals and conferences in the areas that we have discussed and that we will be discussing in future, particularly nanotechnology. It's an emerging area, and people are constantly discovering as they go along. So the problem in nanotechnology is by the time you publish a textbook, it's already obsolete, because the technology is moving so fast. So really the only way to keep on top of nanotechnology is to read current papers, and I certainly encourage you to do that wherever and whenever possible. Okay, let's stop at that point. Any questions? Great, I'll see you at the next lecture then.